Explain the Bragg's spectrometer. Consider a narrow beam X-ray and a crystal. When we rotate the crystal, we observe that the intensity of reflected X-ray is high at some angles and the intensity is weak at other angles. To examine the intensity of X-rays reflected from the crystals at various angles, William Henry Bragg developed the X-ray spectrometer. Let's first understand the setup of an X-ray spectrometer. It consists of an X-ray tube, a crystal, a circular rotating turntable, a rotating ionization chamber, and 3 slits. Ionization chamber consists of gases with an electrode connected to the galvanometer to pass the reflected X-ray through the ionization chamber. Circular turntable and ionization chamber are linked together in such a way that if the ionization chamber is rotated by an angle of 2 theta, then the turntable should rotate by an angle of theta only. The angle of rotation of the turntable and ionization chamber is measured through scale V1 fitted on the turntable and scale V2 fitted on the ionization chamber. Let's now understand the working of an X-ray spectrometer. First, the X-rays produced by the X-ray tube are made to pass through the slits S1 and S2 to produce a narrow beam. Then the narrow beam X-ray is made to fall on the crystal mounted on the circular turntable. We see that the reflected X-ray from the crystal passes through slit S3 and from S3 it passes to the ionization chamber. Now due to X-ray we see that the gas inside the chamber gets ionized, causing the current to flow through the electrode. As a result, the galvanometer deflects. Note that the current flow will be large if the intensity of the reflected X-ray is large. Now, when we rotate the turntable along with the ionization chamber and plot a graph between the angle theta and the intensity of current as shown by the galvanometer, we notice that for some specific angles, current shows a sharp change in its value. From Bragg's law, we know that the intensity of the reflected waves from the different planes of the crystal will be maximum when they are in phase with each other. Thus, knowing the wavelength of an X-ray and the angles obtained from the graph for which the current shows a sharp change, spacing between the different planes of the crystal can be obtained using the Bragg's law.